So hypothesis testing has very similar to confidence intervals, right? So that's the good thing. The way I like to look at it is hypothesis testing and confidence intervals are kind of like brothers and sisters. Confidence intervals is where you are the statistician and you're trying to estimate a population parameter, while hypothesis testing is where we think we know the value of a population parameter, but we don't think it's accurate. So a lot of the times, you know, if you're someone that's doing analysis, you'll create a confidence interval to share with everyone about your analysis. And then, or someone's presenting some analysis and you don't think it's correct, and therefore you want to prove them wrong. So therefore you do a hypothesis test to see if their analysis is really accurate. So there's 4 sections to chapter 8. We'll probably get through 8.1 and 8.2 today. Bear with me through 8.1. All right, I'm going to talk about what a hypothesis test is and the steps and the procedures. And again, they're all listed here on my OneNote. And then we'll get into an example. A lot of times my students want me to do an example first so they can see the math. But if you understand the thought process, the math is not too bad. All right, so we'll try to get through the process and then we'll do a problem near the end. And then we'll do plenty more problems in the next couple classes to finish out chapter 8. All right, so when you're doing a hypothesis test, you have and it's very similar to what the sciences do, right? You have a null hypothesis and an alternative hypothesis. In statistics, the way I like to look at the null hypothesis is the null hypothesis is what everyone believes to be true, right? It's what the population believes is an accurate number. When I go to buy a coffee or soda and it says there's 16 ounces of drink in the cup, I'm assuming that there is 16 ounces of drink in the cup. Everyone believes that they're getting the right amount. Well, the alternative hypothesis is what you, the statistician, is trying to prove. It is your claim, right? I don't believe that I'm getting 16 ounces. I believe I'm getting less than, I'm getting more than. So the claim is what you're trying to prove. The null is what people typically believe to be true, right? And so in our book on page 360, it has this flow chart. It has way more steps on the flow chart than I have written here. I've kind of combined some of the steps because I look at them as going hand in hand. But it basically follows the flow chart. I used to say it was 4 steps. I've actually added a few steps just to try to simplify the process a little bit. So step 1 is to define your null and alternative hypothesis and your significance level. Right. This is probably the easiest of the steps. And in my opinion, it is the most important, right? If you're doing a problem, all this information will be given to you. That's why I say it's the easiest. If you are actually doing real analysis, like for your projects, you are the one that's deciding all of this information. So again, this is stuff that you will know up front. You don't have to do any calculations or anything like that. This is something you will know, right? So the null is typically drawn as H0 or H0, right? And again, it usually has colons. And the alternative, in our textbook, they do it H1. I like HA to remind me this is my alternative. So that's a preference thing more than nothing else. So you can either do H0, H1, H0, HA. It doesn't really matter. Just know one is the null and then the other is your alternative. Now, what you're not, a lot of times when I see students do this, they have the null and alternative equal something. The null and alternative don't equal something. They are statements, right? So that's why I put colons. Now what you have to do is you have to figure out what population parameter that you are doing the analysis on. And there's lots of population parameters out there, but the good news is we are going to stick with the same 3 that we have been doing over the last month. So my choices for my population parameters are P for the proportions, or mu for the mean, or sigma for standard deviation. So there's the good news. Nothing new there, right? And whatever population parameter you're using in the null, you have to use that same population parameter in the alternative. So you're going to be a P, a mu, or a sigma, right? Is it a proportion problem? Is it a mean problem? Or is it a standard deviation problem? The null is always equal to what you believe the value of the population believes to be true, right? So if I think there's 16 ounces of coffee in my cup, then I will say the mu equals 16 ounces. That is what the population believes to be true. If I go to Subway and I buy a foot-long sandwich, I believe that the sandwich is a foot long. So that is what people believe to be true. The alternative, right, is where you now get to make choices. Your claim will be it's either less than what everybody thinks to be true, greater than what everybody thinks to be true, or not equal to what everybody thinks to be true. What these two statements, the value that these two statements are set to, though, are the same. So the same value that's in the null is the same value that's in the alternative. The only thing that you have to decide is what inequality to use. And you decide what inequality to use based on your claim, right? So two decisions here. What population parameter are you doing a hypothesis test on? And what inequality is based off your claim? And again, for testing purposes, this will be all in the problem. For your projects, you will decide this. We'll get to significance level here in a minute, but that's kind of part of step one. Then, step two, calculate your test statistic. So, as always, we go to our lovely pullout. And if we look at our lovely pullout, or if you don't like to use the pullout, go to page 362 in the book, has them all as well. So you go to your pullout, you find chapter 8, test statistics, one population, and you see there is 1, 2, 3 formulas there that say test statistics, right? So just like for confidence interval, the Z is for proportion. Chi-squared is for standard deviation and variance. And then the mean, we have two choices again. We have the T when sigma is unknown, and we have Z when sigma is known. And which one are we always going to use for the mean?
Unknown.
The unknown, the T, perfect. So the good news so far, the only thing we've learned new is some new terminology here, and we have to pick these three red symbols. The distributions we used in chapter 7 are the same distributions we're using in chapter 8. The same tables go with the same populations, parameters, and how you tell which table to use, the letter that it's equal to tells you what table. So you see proportion is equal to Z for the Z table. The mean is equal to T for the T table. And the standard deviation and variance is equal to chi-squared for the chi-squared table. So we'll get into calculating test statistics here in a second. And you know which test statistic to pick based on the population parameter that you picked in step 1. So again, this is why I say step 1 is the most important, because step 1 is going to tell you what to do in step 2. Then our favorite thing to do that we've been doing for a while now, we get to draw pictures, right? So I'm going to draw 3 pictures here. And I'm just going to make them all bell-shaped because the Z and T are both bell-shaped and the chi-squared is kind of bell-shaped. So 3 different pictures. Let me erase this guy because I don't want it over my words. So I do it again. There we go. Right? So we have 3 distributions. And the reason I drew 3 is we have 3 options for our claim. We can have a less than claim, we can have a greater than claim, and we can have a not equal claim. If I am less than, which way am I coloring?
To the left.
Perfect. To the left. If I have a greater than, which way am I coloring?
Right.
To the right. And if I am not equal, I have 2 tails just like a confidence interval. So this is why I was really careful when we got to the t-table and I had you all label your little charts, right? And I said, make sure you put a little note that the alpha over 2 and alpha are for confidence intervals only. Because in hypothesis testing, now you look at your claim. If it is less than, that is a one tail. If it is greater than, that is a one tail. If it is not equal to, that is a two tail. So be careful with your symbols from confidence intervals in here, right? The words tell you which to do versus the symbols like in confidence intervals. So fourth step, calculate your p-value or critical value, all right? This is kind of the, well, somewhat new thing. We've done critical values, right? Critical values are confidence intervals. And critical values for confidence intervals and the critical value for a hypothesis testing is the exact same thing. P-value is kind of the new thing here. It is a probability, all right? And we'll do a p-value today. P-values are probabilities, and using the tables, the only one that actually has probabilities in it is your z-table. So therefore, the only p-values you can find in using the tables is the z. Your t-table and your chi-square table is nothing but critical values. So to find p-values for those type things, we have to use technology. So we'll get into that a little bit. The key here is a p-value. The p-value is the probability of getting the test statistic in step 2, right, based off your sample, given the null is true. So you can see we have this lovely word given, which hopefully brings some of you back to chapter 4. Good news is you don't have to go all the way back to chapter 4 to do all the calculations, but you can see chapter 4 is partially in this chapter because we have that lovely word again, given, which means given knows this has happened. We know the null is true. So what is the probability that we got the results we did in our sample, all right? So that's what a p-value is. So to determine your, step 5 is determining your conclusion, right? Your statistical conclusion based off your calculations. Now, I like the p-value method because the p-value method is one rule, well, two statements, but one rule, and it works every single time. The only issue is to use this rule, you have to know your p-value. So if your p-value is less than or equal to your level of significance, you reject the null. If your p-value is greater than your level of significance, then you fail to reject the null. If you don't want to use p-values, we will use critical values, and we can find that answer using our pictures. So step 5 will come up with a nice conclusion. And then step 6, the final step, interpret your results back to the claim, right? And this is very similar to when I was writing out the confidence interval in a statement. We will take our problem and go back to what we were originally talking about and put it in proper grammar, hopefully, right? Because what step 5 is, step 5 just says I reject or I do not reject, or I fail to reject. You know, if I'm doing analysis from somebody and I go back to them and say, here's your results, I rejected the null, they're going to look at me like, what are you even talking about? So that's what step 6 is. Step 6 is, hey, I need to take all my statistical calculations and put it back into words that the person I'm doing the analysis for can understand. So there's the 6 steps, right? And we'll do a problem. I know most of you are probably dying to see the math, but bear with me, right? So step 1, define your null and alternative and pick your significance level. Step 2, go to your table and pick out the correct formula. Right. Step 3, you get to draw your picture. Step 4, we will either find the p-value or critical event. Step 5, what is your statistical conclusion? And step 6, how do you interpret your results? Any questions on the steps? I know no numbers yet, but any wording that seems different to you? All right. So let's talk about the one thing we haven't talked about yet, right? Are some errors. And this will now we finally get to our significance level. So a type 1 error is represented by our friend, the alpha, right? What is alpha again? Oh, we forget. Chapter 7. How do we find alpha?
It's the tails, so it's
Perfect. Alpha is
Alpha
the tails in confidence intervals, right? Good job, Ben. So alpha here is the same thing, right? Alpha is what percentage is in the tails. And we know how many tails we have based on our drawing. If it's a less than, alpha is all in one tail. If it's greater than, alpha is all in one tail. If it is a not equal to, alpha is now back to two tails, so I'm back to our friend alpha over 2. But alpha is the tails. Keep that in mind. Alpha is the tails. Remember, in confidence interval, that we called our bad region. That was outside of our confidence limits, right? Alpha is still the same here. It is where the bad region is, right? So we have to figure out where the bad region is. And we call that basically our significance level. And you will pick this as the statistician. Now on the test and in the homeworks, it will be picked for you. It'll be in the problem. It will say using this level of significance. In real life, you have to decide what level of significance you want to use. And again, how do we find alpha? We know it's in the tails, but we find alpha by doing what? It's 100 minus what?
Not the critical value, but the percentage in the middle. Whatever
Yeah,
it's called.
your confidence interval percentage, right? Your alpha is 100 minus whatever confidence interval percentage you had. So if we have a 90% confidence interval, my alpha is
10.
10. So your significance level is based off how confident you want to be. So typically alpha is a very small percentage, somewhere 10% or less, right? Because we want to be confident. We don't want to say, all right, I'm going to report my results at a 50% confidence. You know, so typically our confidence, we want to be 90% or higher. So typically alpha is some 10% or less. But it actually means more than tails, right? It is the probability of rejecting the null, given the null is true. So since you pick this, you already decide what percentage I want to reject the null at, right? And we call that a type 1 error. A type 2 error is beta, which is failing to reject the null, given the null is false. And we can actually mathematically calculate these. We are not going to due to time, nothing else. Most of you are capable of doing this, but we're going to just not worry about calculating these. The big takeaway I want you to realize here is alpha and beta are not complements of each other, but they are ratios of each other. So as alpha gets bigger, beta gets smaller. Vice versa, as beta gets bigger, alpha gets smaller, right? And that's extremely important for our little errors in testing here table I got built for you, right? So the way you interpret this table is in step 6, you make a decision, right? To reject or not reject the null. Actually, really, you make that decision in step 5, so I'll put a 5 there. So you make a decision based on your analysis. Now, if the null is actually true and you rejected and you do not reject the null, then you made a correct conclusion. However, if you do not reject the null, but the null is really false in the real world, you just made a type 2 error. Now, if I reject the null and the null is actually true, I just made a type 1 error. Versus if I reject the null and the null is false, then I made a correct conclusion. This is where it's difficult in the statistical world, and this is why this table helps you decide what type of error you made, but it's something that kind of takes a little bit to get your head wrapped around. You will not know if you made an error. All you will know is if you did make an error, what type you made, right? Because you will not actually know what the true population parameter is. So you really don't know if the null is fully true or not. Because if we knew what the true result was, there would be no point of doing hypothesis testing, right? So the reason for understanding this is we use this a lot of times in the real world, right? So a perfect example of this is the United States court system, right? When someone goes to trial for a crime, they are typically judged by a panel of their peers, right? And if most of us probably haven't been on jury duties, I haven't been on a civilian one, I've been on a military one before, but to find someone guilty of a crime, you have to say you're confident without a reasonable doubt, right? And then they say, if you have any doubt, you're not supposed to say someone's guilty, any reasonable doubt. And the reason for this is statistical analysis, right? Back when they came up with this, they understood this error technique. So if our null is the defendant is not guilty, and the alternative is the defendant is guilty, right? If we're at court and we say a defendant is not guilty, that's the conclusion that the jury comes with, right? Not guilty. Then that means we did not reject the null. And if the person is truly not guilty, like they really didn't commit the crime, then we know we were correct as a jury. However, if we say someone's not guilty and they actually did do it, and of course, the only people that really know if someone committed a crime or not is the people on trial. They know if they did it or not. Then the jury just made a type 2 error. In other words, they let a guilty man go, or guilty person go free. On the vice versa, if we say someone's guilty and they really are guilty, then we made a correct conclusion as a jury. However, if we say someone is guilty, but they are really not, then we just send an innocent person to jail, right? So by putting in the things of reasonable doubt into our judicial system, we have lowered, our alpha. We've lowered our level of significance, so that is a smaller chance that an innocent person goes to jail, and we increased our beta, which means there's a higher chance that a guilty person gets to go free. And we're not a political science cast. We can definitely get into all the issues with the judicial system. But if we actually follow the statistical analysis, our system is good. The problem is it's run by humans who have biases, and we mess up the whole thing like always. But statistically speaking, it is designed around the hypothesis testing in this type of table. So I know no math here, lots of terminology and just information thrown at you for the last half hour-ish. Any questions though before we go to a problem? All right, I'm gonna take that everyone's okay then. So let's do a problem then. So 8.2 is doing a claim about a proportion, right? And so the requirements are on page 374 in your book. And I have them listed here. So the requirements to do a proportion problem, you have to meet these 3 requirements. 1, it must be a simple random sample, right? Which takes us all the way back to chapter 2. So remember, a simple random sample means that every part of the sample has the same chance of being selected. Requirement number 2, the conditions are binomial. So now we're back to chapter 5, right? 4 requirements to be binomial. You must know how many trials that you're picking, which means I must know my n. The probabilities of success must stay the same, right? Which means I know my p. They must be independent of each other, which makes my p stay consistent. My 2 options are success or failure, right? And if I have those 4 requirements for a problem, then my conditions meet binomial. And then our 3rd requirement, which is very similar to what we discussed in section 6.6, if I take n times p, it has to be greater than or equal to 5, right? So I take how many trials and multiply it by success. That number has to be bigger than 5. And I have to take my number of trials and multiply it by q, which is my failure. And that also has to be greater than or equal to 5. And if I do that, well, if all these requirements are met, then that means I can do a hypothesis test on a proportion problem. So if I go to the pullout, and I'm on chapter 8, test statistics, 1 population, proportion problem, my test statistic is Z equals P hat minus P all over the square root of P times Q over N. Now, on the sheet, it doesn't have parentheses. However, I highly encourage you to add them. That way, it reminds you, you must do the subtraction before you do the division, right? We have to do subtraction before we do division. Now, we've seen this formula before, right? P hat, at least the denominator, right? In confidence intervals, it was P hat Q hat over N, and then take the square root. Here, it's PQN, and then take the square root. In confidence intervals, we don't know the true proportion, the true population parameter P. So we estimate it by finding a sample and finding our lower and upper limits. In hypothesis testing, we think we know P, and we want to know how accurate it is. So therefore, we take a sample and find our P hat. So the symbols, no new symbols here. It's the same symbols we used in 7, same symbols we used in 5, right? So the good news is our symbols are the same. So if you know your symbols, it's just putting the numbers into the formula and making sure we can calculate it correctly. Any questions on the formula before we go through all 6 steps here? All right, so here is our example. According to a statistical abstract of the United States, in 2000, 27.6% of Americans 55 years of age and older utilize the internet. A researcher believes the proportion of Americans 55 years and age or older who utilize the internet is higher than 27.6% in 2010. All right, what type of problem do we have here?
Proportion.
And how do you know that, Ben?
It says proportion right there.
Perfect. Don't overthink this, right? This says, come on, Heiler, find another straw. It says proportion in the problem. So we know that this is a proportion problem, right? So let's do step 1, which is part A in this case. Determine our null and alternative, right? So I have an H naught, colons. I have my HA, colons. And what is our population parameter? What is the symbol for proportion? Our friend the P? Yes. So we have our proportion P. There's our symbol because of a proportion problem, right? If you forget this, again, go to your little symbols chart. The null is always equal to. And what is the null equal to in this case?
The 27.6% Americans using internet more.
27.6% of internet. Now, what I always do, as soon as I write that value there, I also write it below, because the null and alternative have to be set to the same value. So the null and alternative, they have the same population parameter, they have the same value. The part that we now have to decide for our alternative is what inequality do we use?
Greater than.
Greater than, right? P is greater than 27.6% because of the word higher or higher than. So everything is in the problem to do step 1. We have our null. We know it's a proportion problem, so we use the symbol P. The null is always equal to. to the value that everybody believes to be true, and we're basing it off this statistical abstract that says, hey, in 2000, 27.6%. We're assuming that to be true. And then a researcher, us, the statistician, believes it to be higher. So we now are going to do our alternative. This is our claim that it is higher than this. Any questions on step one, on how I came to finish my null and alternative? It is truly just pulling out the information from the problem. All right. So moving on to step two. Suppose a sample data of 100 people from 2010 stated that 31.75% of people over 55 had access to the internet, right? So now I go on to step two. So I go to my little pullout. I'm doing a proportion problem. So my formula is Z equals P hat minus P. I add the parentheses all over the square root of P times Q times N. And now I just start substituting numbers in. What is P hat?
Sample proportion. Oh, wait, no, I'm wrong.
Yeah, no, you're correct. As always, doubting yourself. It's my sample proportion, which is based off the 100 people. So that is my P hat. So I put in I got to put in decimal form so I can actually do calculations in my calculator. 0.3175. What is P?
Is it that 27.6?
It is. That is why step one is so important. Step one, 27.6. It says it right here. P equals 27.6%. So your claim tells you, I mean, not your claim, your null, sorry, tells you what P is. So I put in 0.276 over the square root of P, 0.276 times Q. How do I find Q?
Subtract P from 1.
Yeah, so 1 minus 0.276. And then N is how many people I talk to. And I talk to 100 people, if I remember correctly. Yeah, right there, 100 people. So there is my N. So now I grab my handy dandy calculator. And I do parentheses, 0.3175 minus 0.276 divided by the square root of 276 times parentheses 1 minus 0.276 divided by 100. And I get a Z value of 0.928. And I'll give a minute, so see if other people are playing along and see if they get the same thing. No one's agreeing with me yet?
Yeah, you're right.
Okay. All right. I was trying to check my calculations here, but mine, something's wrong with my other calculator. I was trying to do it on 2 calculators, make sure I got this right this time. Something's wrong here. So no one has any questions?
None over
All
here.
right. So we're good. So what do we do with that 0.928? What is that 0.128?
Is that your, why can I think of this? Confidence interval?
And it's close. It's a z-score, right? So now we go to our table and we find 0.928. Right? So where do we go to find 0.928? Oops.
$1.46.
So remember, this is a z-score. So let's go down here. Let me scroll down a little bit. We draw our picture. This is a z-score, so I know it's centered at 0. That is, remember, our z-scores are 2 decimal places, so 0.928 becomes 0.93, which means that is right here, about. I draw my line up. I am doing a greater than problem, so I do what? Color which way?
To the right.
I color to the right. So now I do what? I go find 0.93 in my table, and I get what value?
What Ben said, 1.46.
Oh, okay, so he got way ahead of me. All right, so you'd actually go to your table and you'd find, just want to make sure I don't lose everybody. Ben is correct. Sorry, Ben, I didn't realize you gave me the final answer. 0.8238, right? But our table reads to the left, so what Ben and Jacob said, I have to take that answer and subtract it from 1. So 1 minus 0.8238. And I get 0.1762. So you can see, we got to remember how to do chapter 6 here. Now, this value that we just got out of the table, this is our p-value. So when you pull the values out of the table, you have found your p-value. So we're good so far.
Yes.
Yeah,
No.
steps 3 and 4 are basically chapter 6 again.
No, Melissa had a question that I also had.
Yeah.
Where did the 0.8238 come from?
From the table? Am I reading it wrong? 0.93
Yeah.
gives you 0.8238.
The z-score, and you're coloring to the right. Read it wrong.
Am I right? Am I wrong? I could be wrong too. Anyone else getting 0.8238 from the table?
Yes, I just read it wrong initially.
Oh, okay. So then we do 1 minus because we're calling to the right, and we get 0.1762.
Yes.
Okay. Good questions. Yeah, if someone asks me something, I don't hear it because sometimes we're cutting it out because my internet keeps buffing right now. It's like yesterday. So, and for some reason, I don't know if anyone's asked any chat question. I haven't seen anything come up in chat either. Let me shrink this down real quick and see. Oh, I do have all kinds of chats. Why are my chats popping up? All right, sorry. For some reason, usually the chats pop up. I'm sharing my screen, so they haven't. So let me look through some of these questions. All right, so we said greater than because the problem says higher. So we wouldn't want to say, look, we're not trying to prove that the number's smaller. We want to prove the number's larger. So that's where the greater than came from. And let's see what else we got here. Why is the Q uniform 1 minus? Because remember, Q is 1 minus P. And since P is 0.276, Q is 1 minus 0.276. All right, so Melissa answered that. Thank you, Melissa. We're at 0.93 because we had to round because our Z table only had, yeah, so everybody's basically answered all the questions for me. Thank you. Usually my comments pop up when I'm on the screen, but they're not today for some reason.
So the final answer we want here is 0.1762.
Yes.
Okay.
Yeah, if you post in chat and someone's on answer, please respond because usually it does pop up. I don't know why it's not today. All right, so then we go to step 5. All right, so I want to keep this in my view for here in a minute. So remember our rules here on hypothesis testing. Step 5, if your p-value is less than or equal to your level of significance, you reject the null. If your p-value is greater than your level of significance, you fail to reject the null. So we come over here, our p-value is 0.1762. I tell you that our level of significance is 0.05, right? So 0.1762 is greater than 0.05. So therefore, we fail to reject. Based on the rules. Right? If I don't want to find p-values and I want to use the critical value method, then I got to do an extra step on my drawing. So I'll color with blue here for a minute. If I have a 5% level of significance, that is the area in my tail. That is my alpha, right? So if I go to my Z chart and I find 0.0500 in the table, I get a critical value of negative 1.645. So where did I get that from? Find 0.05 in the middle of the table, and it doesn't have one, but it has a little star in its place. Follow the line down, and you get a z-score of negative 1.645. Now, we have to think through this logically for a second. The negative 1.645 is over here, right? However, we are doing a greater than problem, and because my distribution is symmetric, I will put a 1.645 positive on this side because I'm on the right of the 0, so therefore it is positive. And I put it above the 0.93 because 1.645 is bigger than 1.93. So now if I draw my line up and I color this little bit of blue here, that is my 0.05. That is my significance level, right? That is the bad region. That's what alpha is. I'm outside the limits of my confidence. So now if we look at our drawing here, we can see that the red was my shaded region based off my test statistic. And I have red on the good side of the blue, and I have some red over in the bad side. But since all of the red is not in the bad region based on the critical test, I also failed to reject. So no matter which method you use, using the drawing method or the p-value method, you should get the same conclusion. Both of them will be failed to reject. Either compare my p-value to my level of significance, or compare my critical value to my test statistic. And that's what's so important about this. We have to be really careful, right? P-value is a probability. Level of significance is a probability. We are comparing probabilities to probabilities. We are comparing apples to apples. A critical value and a test statistic are events. I am comparing events to events. These are both events. That's why I compare those two things. These are both probabilities. That is why I compare these two things. I must compare the correct things. So which method you use, completely up to you. They both should give you the same results. I prefer the p-value method because the p-value method is one set of rules and always one set of rules. P-value is less than your level of significance, you reject the null. Your p-value is greater than your level of significance, you fail to reject the null. If you like the critical value test, then draw your picture, color your two different tails, and figure out where your numbers lie. Let me go back to Zoom, see my chats. If we have time, but we'll be doing more of these even if we don't get them to them today. So back to my OneNote. So finally to step 6. So home. Let me erase my little black mark there. Come on, erase. Thank you. So step 6, and this one I'm going to type because I can type better than write with my crazy pencil. We have to interpret this back to the original problem, right? So I'm failing to reject. So I fail to reject the null hypothesis. Therefore, there is insufficient evidence to support the claim that people 55 and older are using the internet more than 27.6% of the true proportion. True proportion. So I write it, back to what the original problem was. So there is our fun 6 steps. So to review here again, we take a problem, we read through it, we find our null and alternative based on the problem. We have to pick a population parameter, and the words will either be proportion, mean, or standard deviation. The null is always equal to what everyone believes to be true. Our alternative will be set to the same value. However, we will decide it's either greater than, less than, or not equal to based on the claim or what we're trying to prove as the person doing the analysis. We then will collect some sample data, right? And we will calculate our test statistic. So we go to our pullout, find the test statistic that says a proportion next to it. Then we substitute all the numbers in for the proper symbols and put it into our calculator to make sure we solve it correctly. Step 2 gives us a z-score. So then we round it to 2 decimal places. And the reason we round it to 2 decimal places is because our z-table is 2 decimal places. So we got to round it to 2 decimal places. And then we go find the value in the table, reminding ourselves that z-tables are always color to the left. So therefore, if we're colored to the left, our answer is done. If we're colored to the right, then that means we have to do 1 minus to find our p-value. And then I have to come up to my conclusion. If I use the p-value method, I just take my p-value and compare it to my level of significance, right? And in this case, it's greater than, so I fail to reject the null. Or I could do my critical value test where I go find the critical value and I compare that to my test statistic and my coloring. And I come up, in this case, to the same conclusion of fail to reject the null. And then step 6, we relate it back to the problem we are trying to currently solve at hand. Now, typically, we either reject or fail to reject the null. And this goes back to us statisticians not like to be wrong, right? I either can't prove you wrong, so therefore I say I fail to reject, or I am pretty confident in my calculations, and if I think you are wrong, I will definitely let you know you're wrong, and that's where I reject. I never say that my new value is the correct answer, so that way if someone proves me wrong later in their statistical analysis, I never said that my answer was correct, I just said the other answer was wrong. And how this is applied, right? When people go to court, we never say anyone's innocent. The media does, and people that come out of the courtroom say, but the court of law doesn't say people are innocent. People in the court of law say you are guilty or not guilty, right? So it's just the hypothesis testing built on the same premises, right? We're not proving that we're correct. We're either proving what everyone in the population believes to be true is correct or not. That's why we always reject or fail to reject the null. Right? So I didn't like come up with this new calculation and say, yeah, the answer is 27.6%. I just say there's not enough evidence to say that it's higher. Now, so suppose that it is, all right, what type of error could we have made, right? So now we go back to our error table. So we did not reject the null. And if the null is true, we made a correct conclusion. However, if the value has changed in reality, we just didn't get it in our statistical sample, then we made a type 2 error. So I'll go back to here, my type 2. What type of error may we have committed? We may have made a type 2 error. And again, we will not know if we made an error or not, because we don't know fully if the null is true or not. So there is a complete example of doing a hypothesis test. Any questions on the calculations that we have done here? And I'll go back to Zoom since my chats are not popping up and see if anyone has any chat questions. I do not see any. Wrong button. There we go. All right. So the rest of this chapter is basically doing different types of claims, right? So we will next class continue down this path of doing different types of claims. We may have time to do another quick one if you want to try, but we will be doing more of these examples because the theory of hypothesis testing is not changing. The 8.1, these steps, this theory is the same for all hypothesis tests. The difference is calculating different test statistics. So we will do some mean and some variance and even a little bit with Excel over the next 2 lessons. Any questions?